Well, hey there, good people. Today we are talking about the scientific process, scientific terms, and some of the philosophy behind science. Now, this slideshow that you will see is something that you will see very infrequently in my class. I do not have a lot of slideshows, but my slideshows are always incredibly boring. However, you will find the content is quite fantastic. So let us start working through this slideshow with nice black font on a nice white background. Here we go. The scientific method. What I want to emphasize more than anything about the scientific method, because you've been learning about the scientific method since you were like a little child in 7th grade life science, sitting there learning about all the different steps. What I want to impress upon you more than anything else is that the scientific method is actually kind of a way of thinking. It's something that we should be getting inside of ourselves so that we should become the kind of people who live out the scientific method. Albert Einstein did not get to E equals mc squared by sitting there and saying, yes, what do I have to do first? Oh, I make an observation. Okay, yes, check. And then what is the next step? Form a hypothesis. Yes, okay, and check. No, that's not what he did. He was a scientific person, meaning he was a person of curiosity, and he let curiosity drive him. And the scientific method is what happens naturally if you let curiosity drive you, and if you do that in a systematic way. So we're going to start by talking about the scientific method, and we're going to go through each of these different steps of the scientific method. But what you'll see pretty quickly here is that really it's just what happens if you let curiosity be your guide. I dropped my pen though, so I am going to have to pick that up right now. Okay, got it. Okay, let's go through. The first step to the scientific method is making an observation. It's noticing something about the world. Artists and photographers are actually really, really good at making observation. They notice things all the time. They're trained to see things. They're trained to pay attention to things, to notice things. They are great at making observations and noticing things. The next step is to ask a question based on what you observed. The people who are really, really good at this are kids. Kids are incredibly good at asking questions based on what they observe. One of my little friends, her name is Rain, and when she was 4, and
Jeremiah
pause for an announcement.
Please report to the main office. Jeremiah Gutierrez.
There it is. One of my little friends, her name is Rain. She's 4 years old. And one time I was sitting with Rain, and Rain turned and she looked at me and she said, "Miss Wilson, what is thunder?" And I thought, well, isn't that an excellent question? See, here's what happens. The young people in our lives, all the young kids, are new in the world and everything is unfamiliar to them. And so when they look around the world and they hear something like thunder, they say, "Whoa, what is that?" But the adults have lived in the world for a very long time. And since they've lived in the world for so long, all the things that used to be new and novel and interesting to them, things that they would ask questions about like thunder, they stop asking questions about it because they say, "Oh yeah, that happens when it rains." But kids, no, they ask brilliant questions like, what is thunder? And have you ever actually asked that question of yourself? Like, what really is thunder? And it always comes with lightning. What is that lightning? It looks like a shock, and it seems to have something to do with electricity. And is it at all similar to what happens when you jump off the trampoline and you touch your neighbor's hand and a little shock goes between them? And you know when you do that and you can hear the little pop as the shock travels between you? Is that what thunder is? A giant version of the little tiny pop between your fingers? These are the kinds of questions that kids are asking that people grow old and they stop asking. When I was a kid, I never wanted to grow up. True story, when I was turning 12, it was my 12th birthday, and I decided that instead of turning 12, I wanted to go backwards, and I wanted to turn 10 instead of turning 12, because as an 11-year-old facing a whole like adulthood of losing my ability to see the world with novelty, I didn't want any of that. But instead of turning younger, I decided to become a scientist, because scientists still approach the world with questions, and they're still asking questions about the things that they see. Step 1 is to make an observation, to notice something. Step 2 is to ask a question based on what you observe. My little friend Rain, she noticed lightning and thunder, and then she asked a question about what she observed. She said, "What is that?" The next step of the scientific method is to formulate a hypothesis. It's to give a guess at an answer to your question. Something like, well, maybe thunder is just a bigger version of the little spark that happens between people's fingers, the little pop that happens when I shock myself with some static electricity. In science, a hypothesis has to be testable. So it has to be something that you could actually test in the world. Saying something that is like, saying, yes, the sky is blue because little sparkly fairies dance around and sparkle blue dust and spread out their blue dust everywhere, except these fairies are totally invisible and completely undetectable. That is not a good scientific hypothesis because there's actually genuinely no way to test if there are undetectable fairies flying through the sky. Saying that the moon is white because it is made of paper, that is a totally testable hypothesis. And so that is a totally good hypothesis because we could actually go to the moon and test that. So a good hypothesis in science has to actually be practically testable. The last thing, not even close to the last thing. The middle thing is to design an experiment. This is an opportunity to test the hypothesis that you just formed. So for example, if I said the moon is made of paper, my experiment would involve going to the moon to see if it really is made of paper, or perhaps there's a simpler way that you could test if the moon is really made of paper on Earth. Next is to perform the experiment and gather data. This is where you test the guess that you just made. Whoa, not that, please. How do I go to the next slide? That is what I would really like to do right now. Oh gosh. Oh my gosh. What is happening? Why did we just decide to go insane? Can I just, yep. 1 second. Oh, okay. Well, I guess we're just at the next part now, so that works out fine for me. The next thing is to analyze your data and form a conclusion. In essence, were you right about your guess? And then finally, step 7, if we can get to it, is to repeat. You keep testing your question until you get to a point where you actually can really draw conclusions about what is true about the world. One of my really good friends, her name is Alicia, and 2 years ago she started making sourdough bread. And when she started making sourdough bread, every time her loaf would be a little bit different. She would say, this time the loaf is a little bit too big. She'd say, this time the loaf isn't quite as fluffy as I would want it to be. This time the loaf, blah, 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 blah. And she would have all these different things that she wanted to change about her loaf. Well, what she would do is if her loaf wasn't quite fluffy enough, then she would say, I'm going to try multiple factors, and she would try multiple variables. And she would design an experiment. She would start by formulating a hypothesis. She would say, maybe my loaf isn't fluffy enough because my dough doesn't have enough time to rise. So then she would design an experiment in which she would allow her dough more time to rise. She'd give her dough less time to rise. And then she'd perform this experiment. And she would say, okay, after giving it more time to rise, does my dough turn out to be a fluffier piece of sourdough bread? And then she would analyze when she got her final loaf and formed a conclusion saying, yes, it turns out in fact that my dough does need more time to rise and that does impact the fluffiness. Or those kinds of things. She would try other kinds of things similar to that, but that's the general gist. If you are following your curiosity, like my friend Alicia who bakes sourdough bread, then you are being a scientist and you are following the scientific method. Next, let's talk a little bit about the philosophy of science. We're going to start by talking about the difference between science and art and religion. Here's the truth is that science, art, and religion all have very different purposes. The purpose of science is to answer questions about how the universe works, like why is the sky blue? Or why do all of the planets move in circles around the sun? The purpose of art is to answer questions about the human experience and to express the human experience through various mediums. And finally, the purpose of religion is to ask questions about purpose. It turns out that you actually, look, here they are on the slides. Science answers questions about what nature does. Art is a creative effort to portray the way that things are and to portray the human experience. And finally, religion answers questions about nature's purpose. It turns out that you actually need all three as a human being. All human beings need a system of a way to answer questions about what nature does, like why the sky is blue, or why your coffee isn't as hot as you want it to be, or how your microwave works. These are all questions that science can answer. All people also need the ability to be able to portray the way that things are. And art allows us that outlet, a creative effort. It gives us a way to talk about the way that things are, or even the way that things should be. And finally, religion answers questions about the purpose of nature. Science can tell us that the sky is blue, but it can't tell us why the sky is blue. Science can tell us that we're all here on this planet, but it can't answer questions for you about why you're here or the purpose of your life. That is why I say that even in a public school here, the people who created this public school would still say that you need science, art, and religion. You need all three in your life. Because you need answers to questions about what nature does. You need a creative way to portray the way that things are. And finally, you need answers to questions about why you're here and what your purpose on this earth is. Even if your answer doesn't have anything to do with God, you still need some sort of answer to these questions. You need some sense of purpose in your life. So all three are essential to all human beings. Next, we want to talk about the difference between being descriptive versus prescriptive. Something that is descriptive describes the way that things are. Something that is prescriptive says the way that things should be. Science is strictly descriptive. Scientific laws describe what happens, but they don't make it happen. We can and do make predictions, however, based upon these descriptive laws. Here's the difference. A prescriptive law is something like the laws of driving. If you are driving and you see a red stop sign, then you should probably stop because that is the law. The law tells you what to do. It's a prescriptive law. It doesn't mean that every time every single person in the world ever comes to a stop sign, that person inevitably makes a stop. There's no other way that the universe can exist. That's not true. The legal laws are always prescriptive laws. Scientific laws are descriptive laws. They don't tell things what to do. They describe what is happening. Here I have an eraser. Here's an example of a scientific law. A scientific law would say, hey, if you drop the eraser, it falls. Now, it's not as though science says to this eraser, it's not as though gravity says, all right now, eraser, you know what's about to happen. When you get dropped, it is your role and responsibility to fall. And if you don't, there are consequences for your actions. Possibly fines, possibly jail time. Does that make sense, eraser? And the eraser goes, mm-hmm. And then, when I drop it, in accordance with the rules that it was given, it says, okay, I'll fall. And then it falls. That's not what happens. No, science doesn't prescribe what to do. It doesn't tell the world what to do. It just describes what does happen. It turns out that every time I drop an eraser, it falls, and I drop it again, and it falls, and I drop it again, and it falls, and I drop it again, and it falls. And so we say, that seems to be a law. It seems to be something that always happens. And so then we write it down. Dropped erasers fall, and we call that a law. They describe what is happening. They don't tell things what to do. If this little eraser, if I were to drop it and it were to fly upwards, we wouldn't say, excuse me, Mr. Eraser, but you broke the scientific law, and as such, there will be consequences for your actions. No, we would actually have to rewrite our laws because there would be something about our laws that are not in accordance with reality. So scientific laws don't tell the world what to do. Scientific laws describe the way that the world actually is. Next, skeptical versus open-minded. Here's an important question. Should a scientist be skeptical or should a scientist be open-minded? Think about it for a second. Did you say both? A good science has to be both. Oh, whoops, before we go there. A scientist has to be skeptical because a scientist can't just take everything and at face value and say, yep, for sure, that's definitely true. I believe it. I'm here for it. No, that's the whole point of the scientific method. We're actually going to test things. We're going to ask questions. If somebody introduces a new idea, we shouldn't be like, oh, yeah, totally. I love that one. Let's accept it. It sounds good. I like it. No, we say, no, we need evidence. Show us where the evidence is. A good scientist has to be skeptical, but a good scientist has to be open-minded. Here's the truth, is that a good scientist is always in pursuit of truth. And so, if a scientist is confronted with a new idea, the scientist has to say, let me evaluate that. A scientist has to be willing to sacrifice old ideas in the pursuit of truth. If a new idea is presented to a scientist and a scientist says, I think that actually might be true, they have to be open-minded enough to give up their old ideas in order to embrace the new truth that they are encountering. Next, deductive versus inductive reasoning. Let's define them first, and then we'll figure out which one is science. Deductive reasoning says, suppose that we have a giant idea, a big idea, and then we allow all other principles to flow from that big idea. So, for example, let's say that we had a big idea that said, something like, wow, I'm trying to come up with something on the spot, and for some reason I'm struggling. Okay, let's say that we had an idea, that all pencils that we use should be mechanical pencils. And then I saw somebody who had a regular pencil in the room, a not mechanical pencil, then I would deduce that that is the wrong type of pencil. In other words, I have a general principle, and then I make all the rest of my ideas conform to that general principle. That is deductive reasoning. Inductive reasoning says I make a bunch of observations, and then I use all of those observations to inform a general principle. So, for example, if I walked into a room and I saw that every single person was using a mechanical pencil, and that all of their notes were beautiful and glorious, and that all of their handwriting was stunning and perfect, and then I saw that some other people were using regular pencils, and the people who were using regular pencils, all of them, seemed to be having lesser quality notes. And all of their notes were sloppy, and their handwriting was just an absolute disaster. Then I would say, I've observed this thing to be true in this specific circumstance. I've observed this thing to be true in this specific circumstance. This leads me to make a general conclusion, a general principle, that mechanical pencils are better than regular pencils. Science relies primarily on, oh, wow, look at these. We have definitions. Science relies primarily on inductive reasoning. Notice, deductive reasoning starts with the general truth, and that dictates the truth of the particulars. Inductive reasoning begins with the specifics, which give rise to the general truth. In deductive reasoning, I start with the general truth, and then that tells me what is going to be true in specific situations. In inductive reasoning, I look at a bunch of specific situations, and then after that, I say, oh, this must be the general truth. Science, once again, relies on inductive reasoning because we make observations, and those observations lead us to the general truth. Oh, wow. I should have, really remembered what all my slides look like before we started this presentation, because look, it says which is science, and the correct answer is inductive. Okay, here we go. Moving on. Testability. We got 2 more elements of the philosophy of science, and then we'll talk about the definition of physics. Testability. We already started with this, but we'll review it really quick. For our purposes, in order for a statement to be scientific, it must be testable, which means it must be falsifiable. In other words, you have to be able to prove it false. So, like I said before, the sky is blue because invisible, undetectable fairies are just wandering around throwing blue dust everywhere. Well, you can't prove it is not falsifiable. It's impossible to prove that there are not these tiny, invisible, undetectable fairies. And so that is not a good example of a scientific statement. Saying the moon is made of paper, that is a good example of a scientific statement because you could test that and you could prove that it is not true. Next, whenever we design experiments, it's very important that we have some element of control. As much as possible, an experiment should only test one variable at a time. If Alicia said, hey, I want my sourdough to be fluffier, and she said, so I am going to give it more time to rise, and also I'm going to put it in a warmer environment, and also I'm going to pre-prep my dough with extra salt. If she did all of these things, then she wouldn't know which of those factors actually made her sourdough fluffier. And so experiments test one variable at a time. And that is all on the philosophy of science. Next, we'll talk specifically about a definition of physics. Physics is the study of matter, energy, and their interaction. And that is what we will be studying for the rest of the year. Physics is actually the most basic and the most fundamental of all of the sciences because we're studying matter and energy and their interaction. How matter and energy interact informs all of chemistry, and how chemistry works informs almost all of biology. And so you can see that if you broke it down to what is the most fundamental of the science, it lands at physics. I hope you have a wonderful, wonderful rest of your day, and thanks for tuning in, good people. Bye, good people.